let's go back to what we were talking about at the end last time, which was properties of the absolute value. Properties of the absolute value. And so there are a couple, and I'm not gonna recopy them. Well, maybe I will recopy some of them. I just copied them. So the second set of properties are this: that the absolute value of a product is going to be what? Well, it's going to be the product of the absolute values, and then the absolute value of a sum. What did we say about the absolute value of a sum?
It's less than the absolute value of A plus the absolute value.
Less than or equal to the sum of the absolute values, right? So it's sort of like, can you change the order of the words, right? Here the absolute value of the product is the product of the absolute values. The absolute value of the sum is not the sum of the absolute values, but it's dominated by the sum of the absolute values. Let me just do some examples. If I gave you this, negative 2 minus x squared, you could say, oh, you can actually simplify this quite a lot. You can say, well, look, this is the same thing as the absolute value of negative 2 times, this is the same thing as the absolute value of negative 1 times 2 plus x squared. Right? Just using the properties of numbers, so I factor out a minus 1 here. And then I'm going to use property 2 and say, okay, that's the absolute value of minus 1 times the absolute value of 2 plus x squared. Do you guys see that? Okay. What's the absolute value of minus 1? 1, right? So I can just sort of erase that. And the absolute value of 2 plus x squared? Don't shout it out. Sorry. I should close that. Think for 2 seconds, 5 seconds. Okay, who would like to say? Strong.
Is it just 2 plus x?
It's just 2 plus x squared because?
Because if you take it again, it would be absolute value of 2 plus absolute. Could you look at it that way?
Watch out.
It says, oh, it was x squared. Never mind. Okay.
Right. So that's a sum.
Okay.
Right? You can't say, well, this is going to be. Is this the same thing? Sorry, I'm just going to belabor the point. Is that the same thing as this one? In this case, it is, but not in general. Not in general. Like if I have 2 plus minus 1, that's not the same thing as 2 plus x plus value minus 1. Okay, so, right, we don't have the absolute value of the sum. This is the sum of the absolute values. Right, so we don't want to use that. Okay, but this actually does turn out to be 2 plus x squared. Why? Does anyone see why? So
X squared is going to be positive.
x squared is going to be positive, right? So you're taking a positive plus a positive, right? So you've got the absolute value of a positive number. And so you just erase the sign, erase the absolute value. Okay. Just out of curiosity, does anybody say why? Or do you all say why? Okay, say why. Say WH, why. Are you asking me why I'm asking this? No. Just out of curiosity, does anyone say why? No, you all say why. Just out of curiosity. You see, I think previously people would say why. In my generation, I think people say why. I say why, but my daughter says I'm saying wrong. My 4-year-old daughter says yeah, I say why. Okay, so using the properties, you can see this sort of thing. Another, and this is not really a good example, but if I take, no, I'm not even going to put it up since it's not a good example. But let me say a little bit about this thing, which is called the triangle inequality. Triangle inequality. And I apologize, I will probably throw in irrelevant statements about, irrelevant stories about my daughter, because I always think about my daughter and my son. Because they're always doing sort of funny things, and I feel telling people funny things. Okay, this thing is called the triangle inequality. It doesn't look like there's a triangle involved, right? Where's the triangle? Actually, the triangle comes in when you move this thing into higher dimensions. So there's an analogous statement about arrows, okay? Saying that the length of an arrow, if you take two arrows, U and B, so here is U and here is B, and you create a third arrow, U plus B. This thing is called the sum of these things, which are not called arrows, but vectors. If you take and you look at the size of the sum is dominated by the sum of the sides, right? The size of the sum is smaller than the sum of the sides, right? And that's a geometric fact, that one side of the triangle is dominated by the sum of the other lengths of the two sides, the sum of the lengths of the other two sides, right? So one has this thing, that the size of the sum is dominated by the sum of the lengths of the sides. And one uses a double absolute value in higher dimensions.
Say that one more time.
The size of the sum is dominated by the sum of this. The size of the sum is dominated by the sum of the sizes. Right. Just remember what you know about triangles, that the length of one side is dominated by the sum of the lengths of the other two sides. So that's why this thing is called the triangle inequality. It's just that you're in one dimension, so you don't see the triangles, they're flat. Right. You've got one length of the triangle plus another length of the triangle, and here's the third length of the triangle. It's just flat. Okay. Okay, so that thing's called the triangle inequality. It's really important. I'm not sure if it won't be so important to you guys, but it's actually like a useful tool for mathematicians. Strange. Okay, so now let's recall, we had this thing which we call the geometric interpretation of the absolute value. Rather, of the absolute value of the difference. And this is probably the most important thing that you'll need to know in this class about the absolute value. That there's a geometric interpretation about the distance. What did we say about it?
It's the distance.
It's the distance, right? This thing is the distance between x and y. Right? Right? You can sort of see that, right? Because if x is bigger than y, right? If x is bigger than y, right? So if x is to the right of y, then the absolute value of x minus y is just x minus y, right? Which you see is the distance here. Right? If x is bigger than y, then this thing is just x minus y, which is the distance. And if x is less than y, then the absolute value is going to be y minus x. Right? The guy on the right minus the guy on the left. And that's still the distance. Right? So in either case, you see the distance. So for example, if I write something like -5, the absolute value of -5, one way of thinking about it is that this is the same thing for examples. This is the same thing as -5 minus 0. So you can think of this as the distance of -5 from 0, if you like. If you want. So just a matter of interpretation. Distance of -5 from 0. like negative 5 minus 3, well, what's that in English? Carol?
The distance between -5 and 3.
The distance between negative 5 and 3, right? So maybe I'll get like this, b negative 5, d for distance. And if I make negative 5 plus 3, the absolute value of negative 5 plus 3, well, what's that?
The distance between -5 and -3.
Negative 5 and negative 5. Oops. Right, this is, of course, negative 5 minus 3. In other words, the distance between negative 5 and negative. Yes? Alex?
It's going to be a silly question, but why do you always flip the sign? Just when I looked at it, I thought, oh, that would be the distance between -5 and 3, not -5 and -3.
So remember, distance is the absolute value of x minus y is the distance between x and y, right? As we saw here, right? Yeah, you have to have a minus. You have to have the minus sign here, right? So you want to express this as something minus something else, right? Well, there's a plus here, so I'm gonna be clever and throw in turn that plus into a minus minus, right? So then now it looks like what I need it to look like, x minus 1. So this is the distance between this guy and this guy. Or you could look at it and sort of turn it around, right? Certainly, negative 5 plus 3 is 3 minus 5. 3 minus 5. So I could also say, well, this is the same thing as the distance between 3 and 5. Does that make sense?
Yeah.
Okay. Okay, does that make sense for everyone? Close your eyes for a second. Should I go faster or slower? Should I go faster? Raise the finger if I should go faster. Should I go slower? Raise the finger if I should go slower. Okay, thank you. Open your eyes. Okay, so there's this thing, if you see the absolute value of a difference, then you say, okay, I know this is geometrically. We're talking about distance. Okay, so let me give you another example. If I say something like this, the set of all x, where x minus 2 is less than 1. The absolute value of x minus 2 is less than 1. So you can think about this thing algebraically if you like, you can go to the definition. But actually it's a lot easier to think about this geometrically. Okay, so take maybe 20 seconds and translate this into English, a statement about distance, about geometry. Okay, and maybe turn to somebody next to you or behind you. Turn to somebody behind you. You're always talking to people next to you. Turn to somebody behind you. Oh, no. Behind or in front of you. Okay. who would like to translate this? It's the set of all numbers such that, what? I should have brought my gigantic gun, 20-sided gun. I left it in my house. Taylor.
Yeah. The distance between x and 2 is greater than 1.
Right, the distance, so the distance of x from 2, what, 2 is less than, sorry, is less than 1. Right, the distance of x from 2 is less than 1, so what is that? Here's 2, right, the distance has to be less than 1, so where are we? We're between 1 and 3, right? Between 1 and 3. And we're not inclusive, right? Because if we're at 1, the distance will be equal. Right? So this is it, right? This is the set, right? Let me give you another one. I've already ruined it. If I have something like this, then I already told you, but what is this? You want to say what I just told you? You just include the endpoints, right? The distance could be less than or equal to 1, right? So this would be from 1 to 3 inclusive, right? If I say like x plus 3 is less than 2, then think for 10 seconds. Okay, and then turn to somebody next to you and tell them what it is. So what is it? In English?
Is it just the distance between x and negative?
That's right. The distance to -3 is less than 2. Right? So it's between -5 and -1. Right? And last one. Take 10 seconds and draw a number line and the set, please.
I'm sorry, just,
Yes.
the distance to -3 is less than 2.
That's right.
Is less than 2.
Mhm. Okay. So,
The distance between x and -3 is greater than or equal to 2.
okay, so what does it look like?
So that looks like
The distance from x, you just said in English, the distance to -3 has to be greater than or equal to 2.
so between x and I don't know, between -3 and
Okay, everybody turn to somebody next to you and talk. Talk for 30 seconds.
Ask you two of them, so that you know what has to be. So you can be -5 or, and we're past -5 or I'm past 1. Is that right? Yeah, and then so it should look like that.
Okay, who would like to second? Who would like to second? Start.
I'm not sure, but I understood a little bit from it is that whatever the points are, it would be inclusive.
That's right, so it'll be
Points would
inclusive.
be included, but I don't know what the points.
So just think what this is in English. I have to be farther than 2 units from negative 3. Everybody who's farther than 2 units from negative 3.
So,
So here's negative 1, say,
and negative 5.
and here's negative 5.
And that would be with the golden dot and then going either way because it's.
Going upwards, exactly.
Yes.
Exactly, that's the one. You got the hard one there. You got the tricky one. Right? Because you have to be farther than equal to 2 units of distance. Yes, go on.
Why is it something you said way back?
It's this thing again.
Oh, okay.
You want to put it in,
Yeah.
you want to think about it as an absolute value of a difference, right? So this is absolute value of a difference. If you want to think about this as distance, and you don't have to, but if you want to, and it's just, as you see, it's sort of fast. It's very fast to do this problem if you think of it this way. Is everyone all right? Anyone confused? Sorry, yes.
Could you please just explain one more time?
Yes, yes, absolutely. So right here, we're asked, what is this? What x satisfies this relation? And we say, okay, I don't want to think about the definition. You know, is x bigger than negative 3? Or I'm not going to think about it. I'm going to think about this as distance. So this is the same as x minus minus 3. And so I say, this is the same thing as the x such that the distance of x from minus 3 is bigger than or equal to 2. Okay? The distance from x to minus 3 is bigger than or equal to 2. And then you think about that, like the distance to minus 3 has to be bigger than or equal to 2. Well, here is where it's equal to 2, right? Here's where the distance is equal to 2, right? And the distance has to be bigger than that or equal to that, right? So we have to be farther. It's like everybody has to stay 2 feet away from you, right? Well, it's going to be, everybody's going to stay, there's going to be like this boundary, this barrier around minus 3. Right? If this were in the plane, for example, right? If we were talking about, we have some point, and the distance of x from that point, x naught, say, it's got x naught, has to be bigger than 1, say. Well, then there would be this circle of radius 1 around it, right? And everything on the outside would be the set. That's how it would be in higher dimensions. So it's just, everybody's staying away from minus 3. Minus 3 is being excluded, shunned, bullied. That's not true at all. Maybe minus 3 likes to be by itself. Okay, so let's go on to section 1.3. This is called equations. And I'm sure that you know all of this, but we're gonna go through it in a very sort of step-by-step manner of defining everything. Okay. So just let's recall some terminology. And again, this will all be in the notes. So if you don't want to copy it, you just want to watch, that's a good way. Okay, so we have these mathematical expressions. So like one has, so in the mathematical expression, for example, 3 3x plus 7, x squared plus 1 over x, etc. We have these terms like domain. So domain for us means the set of all acceptable x, right? And by acceptable x, I mean the x for which the expression makes sense. So for example, if we're talking about 1 over x, then the domain doesn't include 0, right? Because 1 over 0 doesn't make sense. So the set of all acceptable x. We call constants any numbers which remain fixed. Any numbers which remain fixed, even if we don't know them, even if unspecified. So like you could have something like ax plus b, right? And the a and b are fixed. Those a and b are constants, even though we don't know which constants they are. And 3 variables are the things which vary. Quantities, any quantity whose value is not fixed. Any quantity whose value is not fixed, a variable. Variables. And the convention since the Middle Ages has been that one uses letters at the beginning of the alphabet for constants and letters at the end of the alphabet for variables. Okay, that's just how they did it in the Middle Ages, and it's sort of stuck. Okay. When we demand that one expression equal another, we have an equation. We have an equation, for example, 3x plus 7 equals 0, right? We say we want 3x plus 7 to be equal to 0. We demand that these two guys be equal. This thing's called an equation. I'm sure you know it. Right? Things like this, ax plus b equals 0 is called a linear equation. Things like this, ax squared plus bx plus c equals 0 is called a quadratic equation, right? It's got a square. If there's a square involved with the variable and lower order terms, then it's called a quadratic equation, etc., etc. There are cubic equations, quartic equations, quintic equations. That's about the end. Yes. Yes, of course. Okay, and of course, as you all have played this game many times. There's the game of solving equations, right? So given an equation, you have to determine for what x is the equation true, right? You have to find the solution set, right? All the x for which the equation is true, and you find out who satisfies the equation, right? And you do it. How do you do it? Usually by simplifying the equation. Simplifying the equation using some legal moves. So you're allowed to do certain things to the equation without changing without changing the solution set, right? And those things are basically the following. So legal moves include number zero, just using properties of numbers. Right, just like adding, using basic arithmetic properties of numbers to simplify. One, excuse me, adding the same quantity to both sides. 2, multiplying both sides by the same quantity. So 0 is sort of obvious. 1, if you add the same quantity to both sides, you don't change the solution. 2, if you multiply both sides by the same thing, you don't change the solution. I'm lying to you, actually. This is not quite right. What's wrong with the second statement? Am I allowed to multiply by anything? I can take let's see, 3x plus 7 equals 0. Equals 6x. Am I allowed to multiply both sides? Yes, no.
You can't multiply by 0.
You can't multiply by 0. So it has to be a non-zero by the same non-zero quantity. If I multiply by 0, that sort of it makes everything an adversary, which would be nice, but it's not true. Okay. And this is a game that we played many times. Let me just formalize it. Let me just make it a little bit formal. So, right. So solving equations. Here's an example. Any questions? Solving equations. Here's an equation: x over 3 plus 2x over 5 equals minus 7 over 5. Right? And somebody says, "What x make this true?" And what would you do? What move would you make? Sorry.
You start simplifying it, so you take the common denominator.
Okay, so you can make a common denominator. So this is maybe property 0, right? Like properties of fractions. Let's make a common denominator. So this, I'm going to say this. This is the same thing as this. When I read this double arrow, I mean that the equation solution set hasn't changed, or it's the same thing. It's equivalent to it. So this property is the fractions. And then go ahead.
What I used to do is I usually make it one fraction, so it would be like 11x by 15 equals negative 33 divided by 15.
Sure.
And then you could cross multiply, so you get 11, so you get 11x times 15 equals to 15 times negative 33.
Okay, instead of saying cross multiply, I'm going to say that we're going to multiply both sides by the same number.
Okay.
It's the same thing. Just do. So I'm going to multiply both sides by 15. So multiply both sides by 15. And same non-zero number, right?
And you just make x equals negative 33 divided by 11.
Okay, so the same thing. I'm going to multiply both sides by the same number. And I'm going to multiply both sides by 1 over 11. Right? And so you get that x is negative 3. Right? Okay, just, I know you may seem like, what is he doing? Why is he doing this? Okay, let me, so just reinforcing the idea that we have to stick to legal rules. Okay, so let me give another example. 1 over x plus 5 equals 2 over x minus 3 plus 2x squared, 2x plus 2 over x plus 5 x minus 3. Okay. So same sort of thing, right? But slightly more complicated. Okay, and take 1 minute and see if you can figure out what the solution set is. And be conscious of what properties you're using, what moves you're making. Okay. Who would like to? Wait, people are still thinking about. Actually, let's okay. Everybody stop, and we'll just do it together. What do you want? What would you like to do? What's the first thing? What's the first move? Somebody raise your hand and say, suggest a first move. Sophie.
Multiply 1, so multiply the first one by x minus 3 over x minus 3.
Okay.
And the first part of the second side, x plus 5 over x plus 5.
Okay. So you multiply everything by 1. That's certainly legal, right? X minus 3 over x minus 3. Right. X plus 5 over x plus 5. Okay. So, right, that was okay as long as x was not 3 and x was not negative 5. Right? Because in those cases, if x were negative 5 or 3, we'd be in trouble. Right? This wouldn't be 1, but rather it would be 0 over 0, which doesn't make any sense. So we multiply numbers by 1. Multiply by 1. It's okay as long as x is negative. X is not 3 and x is not negative 5. Okay. Is that okay for people?
Mm-hmm.
Okay. And then where would you go? Laura?
You could add the two that are So you have the same common denominator, so you have the 2 on the right side.
Okay, so on the right side, we get this 2x plus 10 plus 2x plus 2, everything over x minus 3, x plus 5. And then on the left side, I get this x minus 3. Okay. Chandra?
I'm sorry, should we go back to the second step?
Yeah.
Multiply by 1?
Yes.
On the right side.
So just basically what you're doing is finding a common denominator. Right? This is defining the common denominator trick. So you multiply this thing by, right, here's what's the common denominator. Well, it's x plus 5 times x minus 3. This time we need to get an x plus 5 on the bottom. So we put an x plus 5 on the top and the bottom. That's okay, because if you multiply by 1, it's still okay. As long as this already was a 1. Similarly here. We multiply this guy by x minus 3 over x minus 3. Or, I guess another way we could have done it, and is just multiply both sides by x plus 5 times x minus 3. Right? You could have said, take x plus 5, x minus 3 times the left side, and then x plus 5, x minus 3 times the right side. Right? And that would clear out the bottom and give us the same thing. Anyway, we'll keep on doing this. Okay, so Sophie, what did you do after you did that, after you multiplied that?
Then I just will skip some steps. So
Okay.
I went straight from there to just taking away the denominator.
So you just said, well, let's just
I mean,
erase
it's
it.
not taking away, but I multiplied it all by the same.
Yeah, so that's what you did, right? You cleared, you said, let's multiply both sides by x minus 3, x plus 5, right? So multiply both sides by the same thing, so multiply both sides by the same x minus 3, x plus 5, right? And you get x minus 3 is equal to 2x plus, sorry, let me just simplify, 4x plus 12. Right? And then you can subtract the same thing from both sides, right? I subtract x from both sides. I subtract, say, 12 from both sides. Right? Subtract x minus 12 from both. Okay. And then multiply both sides by the same number, and you get that x is negative 5. Okay. Now let's go back and does x equal negative 5 work here?
No, because the 1 over x plus 5 is 0.
That's right. So the answer, so you end up with something that actually is not a solution. So it's not a solution. Okay, and there's sort of two ways you can think about this. First is, so the book makes this statement, multiplying by expressions involving the variable may introduce what they call extraneous solutions. So like fake solutions, extra solutions. So at a couple points, we multiplied by things involving the variable, and it turns out that we introduced this fake solution that didn't work in the original. Okay. Another way of saying that is that when we multiplied by this thing, we had to make sure this move was only legal if these things were non-zero, right? We could only make these moves as long as these things were non-zero. So at that point, whenever we multiplied when we multiplied both sides by this, we imposed another constraint. That is that x couldn't be 3 and x couldn't be -5. Okay? So we had to keep that in mind. When we got to the end and saw x was -5, we immediately say, oh no, that's not possible because we assumed that x wasn't -5 or 3 along the way. Okay. So just keep that in mind that when you when you're multiplying, you have to make sure that the thing is non-zero. Or if you want to make it Book's way, when you do this, check at the end to make sure that you haven't introduced a fake solution. And this is how the fake solution gets introduced. When you multiply by something, and you have to keep in mind that the thing has to be non-zero. Sean?
So then you would extraneous solution of that, do you go any further?
You see, this is the only thing you can get, and it's fake. So the answer is there's no solution. The answer is this, that there's no solution. Okay, sorry to keep you a little bit over. The clock is 2 minutes past, so I kept you 1 minute over.